The purpose of this video is to teach the steps involved in creating a basic assembly mechanism in CATIA. The video will cover the tools and options in the Digital Mockup Kinematics Workbench, a step-by-step tutorial of how to make a mechanism, as well as some visual examples of some of the most useful joints and how they are used. This instructional video assumes a certain amount of experience with CATIA, including skills in basic part design and basic assembly design, as taught in ETech 113. This video will demonstrate how to create a mechanism using parts that are already made. If you are following along with the video, you can find all the part files used in the examples located on the DVD inside of a zip file. Also, feel free to pause and rewind the video as needed while following the tutorial. Before beginning the tutorial, we will cover some simple safety considerations that can help make your CATIA experience a positive one. While working at a computer might seem like a fairly safe, low-risk activity, there are several important considerations to keep in mind to ensure a pleasant and comfortable experience. The first consideration is that staring at a computer screen for extended periods can strain your eyes and cause aches in your head and neck. To avoid this, remember to keep the screen 20 to 40 inches away from your face, and make sure that it is at a distance that allows you to clearly see the entire screen without having to turn your head. Also, the top of the screen should be at or slightly below your horizontal line of sight, so that the entire height of the screen can be viewed without having to tilt your head up. In addition, the center of the screen should be located between 15 and 20 degrees below your horizontal line of sight. Be sure that your chair and seating position allow you to sit straight with your back supported and perpendicular to the ground, and make sure that your forearms are supported comfortably and are roughly parallel to the ground. These posture recommendations will help prevent discomfort and injury that can result from sitting for extended periods. Because working with CATIA mostly involves lots of use of the mouse, be sure to take small breaks every once in a while to give your hand and wrist a rest from the repetitive movements. These breaks can also provide a good time to stand up and look away from the screen, stretch your legs, or walk around. There is one last consideration which concerns your mental health. It is not unheard of for CATIA to sometimes crash or do strange things at very inconvenient moments. Because of this, it is important to save your work often to avoid potentially losing hours and hours of hard work. This simple recommendation can save you a lot of grief and mental anguish. For more information on safety recommendations regarding computers, you can visit OSHA's website and take a look at their page on computer workstations. Let's start with the basics. First, open CATIA and activate the DMU Kinematic Workbench. From here, you can create parts just as you would in the Assembly Design Workbench. In this example, we will import existing parts into the new product by selecting Insert Existing Component and choosing the necessary parts. The parts needed for this example are the handle and the base cat parts. Note that it is not necessary in this case to constrain all of the parts to each other, as they will become constrained as a mechanism is created. Once all the parts are inserted into the product, the mechanism can be started. First, make sure the DMU Kinematics toolbar is enabled. If it is not enabled, then go to View, Toolbars, and select the DMU Kinematics toolbar. Next, click the tool with the anchor symbol to choose a fixed part that will not move in the mechanism. Select New Mechanism and give the new mechanism a name. Now click on the part to be fixed. This is an important step as all mechanisms must contain a fixed part. This step also creates a mechanism under Applications in the tree. With a fixed part within the mechanism, the first joint can now be created by expanding the Joint tool, which is located above the Fixed Part button, and selecting the type of joint desired. In this example, a revolute joint will be used. When the revolute joint is selected, a new dialog box will pop up asking you to choose 2 lines and 2 planes. The line selected here will become the axis of the revolute joint and will create a coincidence constraint between the two parts. Select the axis of the peg on the base part and the axis of the hole in the handle part. The planes will determine the location of the two parts in relation to each other. This also creates an offset constraint, which can be controlled in the offset option. The null offset option positions the parts so that the planes selected have an offset of 0. This is the option that will be used for this example. Select the top faces of the handle and the base to be used as the planes. Creating this joint has added a revolute joint to our mechanism in the tree. Inside that joint are the coincidence and offset constraints. These can now be edited by double-clicking, which gives the option to change the way the joint looks and behaves. For example, changing the value of the offset constraint changes the distance between the two parts once the mechanism is updated. In the tree, we can also note that the number of degrees of freedom of the mechanism are displayed. In order for the mechanism to be able to be simulated, the degrees of freedom, or DOF, must be equal to 0. When working with complex mechanisms with many parts and many joints, eliminating all degrees of freedom can sometimes be the trickiest part. In this example, the way to eliminate our last degree of freedom is to add a driving command to our joint. To do this, double-click on the joint and check the box next to Angle Driven in the Joint Addition window. The limits of this new command can now be chosen in the Joint's Limit selection. The default here is from -360 degrees to +360 degrees, which means the joint will have a range of motion of 2 full revolutions. Click OK, and CATIA will announce that the mechanism can now be simulated. Also, a command was created in the tree, and the DOF is now equal to 0. Now, the mechanism can be simulated to make sure it works the way it was intended. First, click on the Simulation with Commands tool to open the simulation window. With the Immediate option selected, you can drag the slider left and right to change the driven angle command and rotate the revolute joint. If the simulation option is changed to On Request, the angle can be changed, but the joint will not move until the play button is pressed. The mechanism can also be moved by clicking and dragging on the actual model. Before closing this window, it is a good idea to click the Reset button to reset the mechanism to the state it was in when the window was first opened. Now that the mechanism has been tested and it is clear that it works as intended, a real simulation can be created that can be saved and replayed. First, click the Simulation tool on the left and select the mechanism to be simulated. This brings up an Edit Simulation window and a Kinematic Simulation window. The simulation will be created based on frames that are added by pressing the Insert button and can be deleted or modified using the other buttons in the same row. The position of the mechanism at each frame creates an animation of the mechanism in action when played back. By default, one frame is added to the simulation from the beginning. To add another, move the mechanism using the slider in the Kinematic Simulation window, and then insert a new frame by clicking Insert. Next, change the interpolation step size to 0.01. This determines the size of each step created between the frames. The lower the number, the slower and smoother the animation will be. There is also a loop option, which can continuously loop the simulation, either skipping back to the first frame or by reversing the direction of the simulation once it reaches the end. At this point, the simulation can be changed and the frames can be added or removed to create the desired animation. When the simulation is complete, click OK, and a simulation is created in the tree. Simulation can be viewed and edited by double-clicking it on the tree. Next, if we compile the simulation, it will create a replay, which will save the simulation so it can be played as it currently is. First, select the Compile Simulation tool under the Normal Simulation tool. Give the replay a name, select the simulation to be compiled, and then select the desired time step, which is the same as the interpolation step size from before. Now, click OK and the simulation will be compiled, and a replay is created in the tree. Now, by double-clicking on the replay, it can be viewed using the same navigation buttons from before. The same loop options are also available, and the speed can be increased by 2, 5, or 10 times the original speed. Now, no matter what is changed in the simulation or the mechanism or the model, this replay of the simulation will always be there to view and will not change. Congratulations! You have now successfully created and simulated an assembly mechanism in CATIA. At this point, be sure to save the product file. Now let's take a look at some other useful joints that are commonly used in creating assembly mechanisms. A prismatic joint is similar to a revolute joint in that it requires the user to select two lines and two planes. The major difference is that the prismatic joint involves a linear movement in one direction between the two parts. Therefore, it uses a length-driven command instead of an angle-driven command. A cylindrical joint is a combination of a revolute joint and a prismatic joint, which gives the user the choice to create a command that is either angle-driven, length-driven, or both. The prismatic and revolute joints it uses can be created on the fly or can be selected from existing joints. A rigid joint simulates the act of physically securing two parts together. This way, when one part moves, the other part moves with it. A point curve joint is used to guide a part to follow a curve. When creating this joint, make sure that the part contains a point that lies on the curve to be followed. This example shows a mechanism that uses two revolute joints and one point curve joint. A gear joint is a combination of two revolute joints, one of which is angle-driven, and which are connected by a gear ratio that is selected during the creation of the joint. A rack joint is a combination of a revolute joint and a prismatic joint. The rack joint can be angle-driven by the revolute or length-driven by the prismatic. Like the name implies, a cable joint can be used to simulate a cable or pulley type system. It involves creating two prismatic joints with a single command associated with one of the joints, which will drive the cable. With the information provided in this video, you can now explore the digital mockup kinematics workbench and create your own mechanisms or add mechanisms to existing models. Here are some examples of what can be done using joint-based mechanisms.